All right, so this is a review for MSE-280, going over some of the math to use. I'm going off of one of these quizzes here to get some math done. So the first question, steel bar cylindrical, 8 millimeters in diameter, is loaded 1,000 cycles per day with a load of 15,560 newtons. How long until fatigue failure takes place? Stress is equal to force divided by area. I'm going to use the formula. Stress is equal to 4 times force divided by pi diameter squared. This is it's force divided by pi divided by 4 diameter squared, but I just moved to the 4 to the top for this one. So this is going to be equal to 4 times 15,560 over pi times 8 squared. This is going to equal 309 megapascals. One thing to keep in mind is that 1 Newton over millimeter squared is equal to 1 megapascal. So now that we know how much stress it's under, we can go over to our chart here, find where about 309 is going to be. I think it's going to be about here. Going across, we can see there's a point right here, right at 1e to the 6. So that's how many cycles it's going to take before this bar is done for. And we're told that it's placed under 1,000 cycles per day. So you're going to take 1e to the 6 cycles and divide by 1,000. And you're going to find that it's going to take 1,000 cycle or 1,000 days before it fails. So a silicon carbide rotor fractures at a stress level of 150 megapascals. This material has a fracture toughness of 4 megapascals per meter halved. Estimate the external flaw size responsible for this behavior with the geometric fracture of F equals 1.12. Report your size in millimeters. I'm going to use the formula Kc is equal to F times stress C square root of pi times area. Rearrange for area, it's going to be equal to Kc divided by F times stress squared divided by pi. So using this formula, area is going to equal, it's going to equal 4 divided by 150 times 1.12, all that squared divided by pi. And this is going to give you your answer in meters. Don't forget, you still have to convert to millimeters. So I got 1.88 e to the negative 4. So to convert from meters to millimeters, multiply by 1,000. I get 0.18 millimeters, which our answer here is going to be 0.2 millimeters. Moving on, an aluminum alloy will be used in an airplane wing. The alloy has a plane strain fracture toughness of this and fails when a stress of this is applied. Determine the size of the surface flaw that initiate the fracture in inches. Now, the one above was in meters. This one's in inches. And the one above asked for it in millimeters. This one, there's no direct conversions you have to do since it's already inches over here with your Kc. So same formula, Kc is equal to F times OC root of pi A. Once again, A is going to equal Kc divided by F OC squared divided by pi. And in this case, A is going to be equal to 0.0658. And it's asking for the flaw in inches. This is in inches. And going off of our significant digits, the last one only had one, so I'm assuming that this one only will have one. So we're going to go with A is equal to 0.07. I can do the math, but I cannot do the significant digits. And I know that's bad, but I just can't do it. So if that one's wrong, I'm blaming it on the significant digits. A polymer bar's dimensions are 1 inch by 2 inch and 15 inches long. The polymer has a modulus of elasticity of 600,000 psi. What force is required to stretch the bare elastically to 15.25 inches? All right, so a polymer bar's dimensions are 1 inch by 2 inch and 15 inches long. The polymer has a modulus elasticity of 600,000 psi. What force is required to stretch the bar elastically to 15.25 inches? Now, for this one, we're going to use the formula. Stress is equal to modulus times strain. Now, we're going to go ahead and calculate stress. My bad. We're not going to calculate stress. That's the last thing we do. We are going to go ahead and do strain. So stress is going to equal 600,000 times strain. And strain is going to be the change in length divided by initial length. So it's going to be 15.25 minus 15 divided by 15. So 0.25 divided by 15. So this is going to equal 10,000. Now we're asked for force. And we know that stress is equal to 4, or well, actually, in this case, it's a force divided by area. So that means that force is going to be equal to area times stress. So area in this case is a bar. So it's going to be force is going to be equal. The area is going to be length times width, or 1 times 2 times 10,000. Or force is equal to 20,000 pounds. All right. An 850-pound force is applied to a 0.15-inch diameter nickel wire having yield strength 4,500 psi and tensile strength 55,000 psi. So one thing to keep in mind, if the stress is greater than yield strength, it will plastically deform. If stress is greater than tensile strength, it will neck. So we have an 850-pound force and a 0.15-inch diameter nickel wire. So stress is going to be equal to 4 times 850 divided by pi times 0.15 squared. So stress is going to be equal to One moment, calculator issues. Doesn't want to work for me. Stress is going to be equal to 48,100 psi. This is greater than the yield strength, which means it will plastically deform, but less than the tensile strength, which means it will not neck. So will it neck? No. Now, find the percent strain at failure for this steel. Now, all we have to do for this one is, so like I was saying, we're finding the percent strain at failure for this steel. So what that means is it's going to be our calculated strain times 100 to get it to 1%. So at failure, our gauge length is 65.64, and initially it was 50.8. So 50.8 and 65.64. Let me make sure I got that right. Yeah, 65.64. So the difference between these two is 14.84, which is then divided by the initial length of 50.8, which is going to be equal to 0.29 times 100, which is going to equal 29%. I'm just going to go ahead and say 30%. And then here we're going to say 30. All right, question number 7. A typical tensile stress strain curve for a ceramic, a metal, and a slowly loaded thermoplastic polymer. So B is clearly the metal in this case, or the magnesium alloy. The reason being, what a metal will do is it'll increase, reach that peak, which is the tensile, and then it'll experience necking before finally snapping and stopping. Now, for A, that's a ceramic. The ceramic stops right there because it can't really, it's so stiff, it can't handle a lot of force on it, or it just shatters, which is what happened there. And the polymer is going to end up having the longest because it's so elastic. In this portion where it's kind of flat lining, that's when something about bonds, linking, straighter, secondaries kick in, makes it stiffer until it finally reaches a peak and snaps. So this whole region is necking here. Also, oh, that's the wrong one. So alumina is a ceramic because typically you have Ina for ceramics, magnesium alloys, metal, and then that's a weird name. So I'm just going with that being a polymer. So this one here. The following are the load and gauge lengths from a stainless steel. The diameter of the bar is 0.498 inch. Calculate or plot engineering stress versus strain for the data shown. Find the tensile strength for the steel. Report in megapascals. So the only thing I see here that may get you is you're given the diameter in inches. So you need to convert that to centimeters. And I am actually stupid, so I'm just going to double check myself real quick to make sure I do it right. I'm pretty sure it's 2.54 is the conversion from inches to centimeters. So I'm going to double check 0.498. That gives us 1.26 centimeters. Let's see, 0.498 times 2.54. Yep, 1.26. So it is, so the conversion factor, 1 inch is equal to 2.54 centimeters. Now from centimeters to millimeters, you divide by 10. So our answer is going to be, or my bad, multiply by 10, multiply by 10. This is going to give us 12.6 millimeters as our initial length. And I'm going to double check that real quick. Say 0.498. Yep, 12.6, just like I got. Just double checking there. So now I could graph this, but it's a lot easier to just calculate it. And it's asking the tensile strength. So the tensile strength is going to be the max load that this bar has on it, which appears to be right here, 69,670. So I'm going to use my stress formula here, which is going to be equal to 4 times the force divided by pi diameter squared. And this is our diameter in millimeters because it asks for it in megapascals, and you're given it in inches, so you need to convert. 4 times 69,670 divided by pi times 12.6 squared, which is going to equal 558 megapascals. Now, as for significant digits, 4 is our lowest. It only has 1. So we're just going to go ahead and say, but you know what? I don't want to write on there that much. I got 3 there. We're going to go with 3. We're going to leave it as, I'm not good with significant digits. Like I said, we're going to leave it as 558 there. And hope for the best. So coming down here, once again, collected from a 10.84 millimeter diameter test specimen of magnesium. After fracture, the gauge length is 32.61 millimeters. Plot the data and calculate the tensile strength in megapascal. So once again, calculating the tensile strength. Find the max force, which is right here. And we're given our initial 10.84 millimeters. And it asks us for it in megapascals. Newtons divided by millimeters give us megapascals. This is going to be 27 e to the 3 times 4 divided by pi times 10.84 squared. And this is our stress to find our tensile. And this is going to be equal to 292 megapascals. Once again, I'm hoping I'm doing my significant digits right. If not, then I'll be sad, but it is what it is. I'm not that good at it, I'm afraid. And for the final question, a bar of alumina that is 0.3 inches thick, 0.4 inches wide, and 9 inches long is tested in a 3-point bending apparatus with supports located 6.9 inches apart. The bar fails at 93 pounds of load. Calculate the modulus of rupture for the bar in kpsi, which is 10 to the 3 psi, or 1,000. Just give me one moment. Sorry about that. So like I was saying, so here we're asked to find the modulus of rupture. The formula for this is going to be bend is equal to 3 force times L, L being the distance the supports are located apart, divided by 2 times width times height squared. And the height is usually given as thickness. So this one is going to equal 3 times 93 times 6.9 divided by 2 times 0.4 times 0.3 squared. So this is going to give us it's going to give us 26737.5 psi. We're asked in K psi, which is 1,000 psi, so divide by 100, or my bad, divide by 1,000. And our stuff only has one significant digit, and the answer is 26 here, so I'm going to write it as 30, and hope that works. Let's see how it did. All right, so thank you for watching this if you did. I'm going to upload this to YouTube, and I'm also going to send it to Miss Robin. You guys have a great day.